Thanks for joining from across the globe. This is a IPCOS webinar on advanced techniques for well test analysis and model calibration. This is upstream oil and gas, just in case somebody is wondering. Okay, we'll start with the 5 minutes of introduction of IPCOS for those new attendees who have not been in any of them before. And then we will go with the flow of today's topic. IPCOS is a global company. It's headquartered in Belgium. It has offices across the globe. Houston is one of them. IPCOS has unique domain knowledge and process understanding, and it uses that to deliver the projects from end to end. It starts with some cases consulting, leading to delivery, and then supporting it through the life of the project. We have been in the business for more than 27 years. And we have engineers spread across the 7 offices that support projects across the globe. We have done several projects across the globe. Next slide, please. IPCOS is now a member of bigger team, Process Automation Solutions. They have a larger presence across the globe, and it also has offices in a lot more locations across the globe. So with this, IPCOS, today's focus will be on IPCOS's digital oil field solutions. What does that entitle? It entitles surveillance and optimization through process understanding of your asset. We start from all the way from the field, where we digitize and automate their operations and move up the chain, help the engineers to improve and optimize the production, and all the way report and monitor the performance to the management. In the process, we try to minimize the amount of work done by the engineers and field operators as efficient as possible, and so that they can focus on important activities. The key elements of these solutions are getting the data correct, having the models ready to do the analysis, and build some automation of workflows, and then provide insights through visualization and collaboration. Outside of these typical production engineering tasks, the key also is in making sure the data is accurate, either it is on-prem or in cloud. We help with the customers in getting the right data to the right person by integrating seamlessly in the background. So that's a different group within IPCOS, but helps integrated with every other assets, every other project that we have. So next slide, please. So as we were saying, we have many customers across the globe, across the industry. Here is the list. For those who are new to our group, we would like your logo to be on this one. So if you find today's presentation interesting, please reach out so that we can have your logo here. Thank you very much. With this, I will introduce the speaker today. Today we have Irina, who is the digital oil field team lead at IPCOS. She has masters in both petroleum engineering and geophysics. She is experienced in digital oil field consulting and implementation of projects across the globe. Her projects cover various engineering applications such as well testing, allocation, gas lift, ESP, PCP, surveillance and optimization, etc. Today's topic is one of those, and I will leave the floor to her to take it to the next stage. Thanks, Irina, for doing this. Please go ahead.
Thank you, Ravi, for introduction, and thank you, everybody, for attending this webinar. As the name of today's webinar suggests, we are going to be talking about the advanced techniques for well test analysis and model calibration. And if we think about this, why the whole flow is important here? Because eventually we are trying to achieve the goal of having our models up to date and maintained, because in the current digitalization era, models have a very, they have a lot of power as a tool for surveillance, optimization, and forecasting. So historically, when we think about well testing, there was a lot of manual effort involved into keeping the models up to date, and it still is somewhere in some places in the industry. And as the industry is moving more and more towards the digitalization, unlocking the possibilities of automating model-based analysis, it also becomes increasingly important to keep the models tuned and up to date. So with this in mind, our topic of the techniques for well test capturing and model calibration will be put into the context of this automation concept. We will discuss what are the main components of this process, and what are the main challenges and where they reside in this process. And of course, how automation can help and facilitate streamlining this process and making eventually life of engineers easier. And at the end of the presentation, as Ravi already said, we're going to reserve some time for Q&A, so you would be able to ask the questions that you're interested to discuss. So let's discuss what this whole thing is about. Essentially, our task is to perform a well test to make sure that our models are up to date, and they are in line with the measurements that we have, and we can calibrate them if needed. So perform tests, collect the data, and calibrate the model if needed. So if we talk about that on the high level, the components that are involved in this process are, first of all, the field data. This is our historian. Well, this is an industry standard. So basically every oiled field has some sort of SCADA system, and then there's some sort of historian on top of it. And eventually the real-time data are getting continuously written into some sort of data storage, right? Having this data available, the next step is, of course, to actually perform and capture the well test. And at this point, the question is how frequently those well tests are taken, right? And different companies have different commitments. They have different practices that affect the frequency of well tests. And in some cases, it's not even possible to perform a well test. So, but if the well test is performed, it's pretty straightforward. You have your data, you have your well test, you know when it started, when it's ended. You can extract the data, and you can run the analysis based on the data that you extracted from your historian. And then the data needs to be QC'd. And then the question is, who is the main consumer of this well test data? And who is in charge of the QC, how the whole business process is organized? And eventually, the most important outcome is whether this well test that was QC'd by someone, can it be used for model calibration? And then comes the modeling part, which we're going to discuss in a simple term. First, you validate your model against well test data, and if needs to be calibrated, then it needs to be matched to your well test data. And in this whole field of modeling, the biggest question for us is how easy it is to validate and to calibrate the model? How long does it take to gather the data? How long does it take to perform calibration? How much manual effort it takes? And once the model is calibrated and available, then it unlocks the insights into well performance, surveillance, and also unlocks the potential for advanced engineering workflows that are done on those reliable calibrated models. So in this process in mind, where are the most challenges that are very frequently faced? So on the side of well test capturing, the first and obvious one is well test frequency. As we discussed, different companies have different commitments and different operational complications sometimes that don't allow to test the wells. The well test frequency is one thing. Then the data quality is usually a very important factor to be to allow the well test to be used for model calibration. And the common issues could be incomplete or incorrect data, dead gauges, missed intervals of writing the data. And for example, if we talk about the business process of well test QC, the question is, who is the main consumer of the well test? If the well test was generated for another engineering discipline, or if it was generated purely for accounting, the people who do the QC for accounting, for example, would not perform the same type of QC that is required for engineers. For example, the transient behavior maybe could be also captured in this test, which is not desirable for model calibration. So the QC of the well test is usually a pretty time-consuming process, and it gets increasingly complicated when we're dealing with a large number of wells and well tests, and then it becomes increasingly error-prone to have this as a manual process. And also, if we have the well test that goes from different, let's say, databases, if it needs to go a long route before it lands in some system that automates model calibration, how long well test data transfer between the system takes? That's also quite a potential bottleneck. Then on the model validation and calibration side, we are mostly constrained by the time and the value that it generates. So how long after well test is available, how long it takes to calibrate the model when the well test is available. So if the well test just sits there and being unused because engineer doesn't have a capacity to calibrate the model. So how much time it takes, of course, and when the model is calibrated, can more insights be extracted from this model calibration? Can this operation can be contextualized, historized, and is it possible to derive some important intelligence about the well behavior? And again, the main bottleneck in this whole process is engineers' time. And with these challenges in mind, let's discuss why automation is important for that. So ideally, our automation should be covering the whole process, the whole cycle from upstream, from well test capturing to the downstream, to model calibration. So for all stages of automation, what really makes a difference is reducing engineers' hours that is saved on manual actions, QC, calibration, gathering the data, etc. So if we look more into well test QC, the cases where engineers' involvement is still required, they exist. Not everything can be automated, but automation can provide help to engineers, for example, some quantitative information about the quality of well test, highlighting which well tests need attention, which can be automatically approved, etc. And in case of not having a well test point, automation can provide tools to generate those engineered or pseudo well tests that can be also used for model calibration. And on the model calibration side, what automation does is essentially decreasing the burden on engineers by automating all the simple cases and really focusing engineers' time on the cases that require attention, so special cases only. And importantly, this whole chain needs to happen on time. So you receive a well test, it can be quite quickly processed, it can go to the model calibration unit, and it can generate calibrated model quite fast. And then all the engineering workflows that are based on that calibrated model would be more accurate and would generate more insights. And they would also generate more tangible benefits from well testing and from model-based analysis, like potentially to increase the production by optimizing well operations. So now, what are the things that we can actually do to, first, let's discuss improve the well test capturing process and the QC. And let's first talk about the automated well test QC. Essentially, we want to ensure that our well test is suitable for model calibration and spend as little time as possible on this. So in the list of solutions, there are various common statistical techniques that can be used to analyze well test data. Something like standard deviation, error mass, or mean residual, slope, concavity, and other statistical features. And they all can be automated to analyze the test and to indicate important quality factors like that good live sensor data readings are coming for the whole duration of well test, for example, that the transient periods are excluded from the well tests, and only the stable period would be used for model calibration. And also, those well test points can be also put into context of the historical well tests. So the algorithm can also classify tests into good and bad based on how they differ from the other tests historically. And eventually, the automated QC that would be based on some knowledge about the wells, about the field, some custom thresholds, can generate an automation of all the simple cases, and really drawing engineers' attention to the cases that require their time. So this is a first example of so-called operation by exception that really helps focusing engineers' time where it is needed. So now let's talk about well test generation. So in some cases, it's simply not possible to test a well. Best cases out of it is when you, of course, have more advanced instrumentation and BFMs, metered wells, and the test can be generated from your historical real-time data. And for that, it's important to provide engineers with the tools that can be used to generate this well test, QC this, and it can be custom made. It can be a part of out-of-the-box solution provided by industry vendors, but this has to be facilitated this way or another. And in more complicated cases, for example, when you have commingled flow, when there's no possibility to test the well, and different operational issues, there are some other known techniques that can be used to generate some sort of well test point. So the easiest one, I would say, is the simple test by difference. So this is the case when the wells are flowing to the common manifold, and you have the export separator rates metered. And then somewhere in this production history, you would need to find places where one well came online or offline. So only one well changed its status at some point. So this is a pretty straightforward method with its own limitations. Like mostly the physics is not captured there, like back pressures. So all the wells are assumed to be stable at the same time. On the advanced front, there are some techniques that can also make use of virtual metering when generating a well test, but again, it would rely on the models being tuned and reliable. Techniques like commingled flow allocation, which are also helpful, but they might not be unique. So they also use some underlying assumptions. So, and all of these methods actually are pretty data intensive. They require a lot of tests, permutations, in some cases, even the machine learning. So if we take a simple example of the simple test by difference, right, it is also a very data intensive process. So on the screenshot here, you see the records of wellhead pressure, associated well statuses, and the export gas meter, for example. And we have seen the cases when it was manual engineers' tasks to find the periods when there was only one well that came online or offline. But in reality, it is quite simple to automate this process, to have a data-driven analysis of, let's say, pressure, temperature profiles, separator rates to use, for example, pattern recognition to detect the buildups, to detect well events, and to be able to automatically generate those tests by differences, again, with some custom parameters such as the duration of the test, like duration of potential transient period, so the stabilization, et cetera, et cetera. So with having such data-intensive and manual labor-intensive methods that allow generation of well tests, it is increasingly important to automate these. And this would eventually generate a lot of values and saving time for engineers. If we're talking about the previous topic of QCing the test, generating well tests, those pseudo-generated tests can also be, of course, automatically QC'd. And then, as a result, this automation system simply spits out a list of well tests of different origins to engineers, and importantly, only spotlight those that require attention, and let engineers to go through some assisted manual steps to approve them, eventually to send to the model calibration. So now, how we can use automation to play a role in model validation and calibration process. As discussed, this model validation and tuning process can be really time-consuming, and it really starts from gathering well test data, and we will discuss just the simple concept of how this validation and calibration is done. So we would need to gather, as engineers, the produced rates, ratios, downhole gauges, etc., etc. Depending on the lift type, it would be the different set of signals. And then this test data must be plugged into the model to evaluate model deviation against the key parameters, such as produced rate, downhole gauge pressures. Here, in this explanation, I would be mostly focusing on the physical models, for which the matching of the model essentially means the matching of VLP and IPR curves to match the production and to match the rates. So once the validation is done, the well test is classified into the valid or invalid, depending on whether model is matching or not. And if there is no match on the model, depending on a series of custom thresholds, then the model needs to be sent for a calibration, which is, as we discussed, essentially a tuning of VLP and IPR. So now in this process, if the model is still valid, so the well test, it still can reproduce the well test values with a certain confidence, is it even worth checking for engineer that this model is still good? This is something that totally can be automated. And then to automate this process, we first need to visualize it. And yeah, here's how it looks. We initially have a well test data, and ideally this well test data used for model calibration needs to be reliable. So all that we discussed on the previous step, well test QC, ideally should be a part of the same process architecture chain. So the validation process knows what kind of test quality it expects. So also, the new well tests, as they come into some sort of automation system, need to be detected, and this automation chain needs to be triggered. So on the triggering side, depending on the automation system or software that is used, it can be important to really make this process smart, because sometimes the licenses are involved. Sometimes it's critical to have the process running smoothly and fast. So in this case, the triggering is something that really needs to be customized to a specific case. Then the model gets validated, and then if there is a match to a well test, then the model requires no calibration, and it can go through some final QCs and approvals, and it can stay as is and be used for engineering workflows. But if there is no match, the model requires calibration, and the automated workflows can suggest engineers what kind of matched parameters are required. It's not needed for engineers to manually punch in the numbers. Since the machine has done that, engineers would need to review and validate and accept these parameters into the model. And at this stage, it's really important to provide engineers with all the additional information that they would require to make an educated engineering judgment. So we're talking about trends, we're talking about well KPIs that would allow to assess historical performance of the well until this well test point. But in some exceptional cases, the manual intervention may be required. So in this case, this is mostly the cases when the machine is really struggling to find a match, or if the match that is found by automated algorithm does not make engineering sense. And in this case, manual intervention might be required. So if the model was calibrated, and if something critical has changed in this model, some final steps can be also performed, like VLP generation, etc. And final QC steps done again automatically, manually, depending on the process architecture. So this high-level architecture may contain a lot of nuances, depending on the business process that is currently in the client side. But the basics stays the same, and importantly, some generic approaches would always work. So how do we help engineers with this model calibration? To summarize this, we automate simple cases as much as possible. We narrow down the scope of work for engineers, so we spotlight only the cases that require engineers' review. We call this operations by exception. That proves to be very powerful. So by pointing out abnormality, the data issues, non-physical results, we help making engineering judgment. Also, historical trends of well test data, model parameters is really helpful for that. And to wrap it up, I would like to list a couple of points that are very important to make sure this automation process is successful. First of all, the architecture needs to be well thought through, from upstream, from data to the models. And if there are a lot of systems involved, it is important to ensure efficient data transfer between different systems. The data usually is one of the most critical pieces, so smart data mining is crucial. And often it comes hand in hand with openness to change existing business process, because data mining often involves other systems that have been in place at client side beforehand. Also, a thoughtful design of operations by exception, and this involves mostly working with engineers who are going to be end users of the project, and also getting a feedback from them, what would be that critical information that would help them to make engineering judgment. With this, I would like to open the floor to questions. And I would like to thank you all for your attention for this webinar.
Thank you, Irina. Please use the Q&A box to ask the questions. I have one question here. Let me read it out. How to expedite the manual calibration of well parameters resulting after data training and testing? Don't think the question is clear.
Yeah, I'm not fully sure. Are we talking about model calibration?
I'm assuming that. So let's go ahead, assume that, and then answer that question. I mean, typically what you would do is most of the times you go and check automatically to see if the results are good, and the system will automatically can tell you that this particular model you don't have to calibrate anymore. You have to only calibrate those models that are thrown as exception by the system. Maybe that's what I think is what appropriate for this question.
To me, training and testing already implies some calibration. That's why I was a little bit hesitant. Generally, when we're talking about this classical VLP IPR model calibration, this is not a unique solution, of course, but there are also other physical parameters that can facilitate getting to the most appropriate point. So, for example, there's an infinite number of PI and reservoir pressures you can match your model with, right? But you can choose which one is going to match your top-down and bottom-up gradients the best way. So I would say that in this case, you can bring also some supporting engineering analysis, also in an automatic way, that would help engineers to make a judgment about what should be the well parameter results.
Yeah, good. Let me ask you a different question. What are the challenges that you face in automation?
Well, the biggest challenges that are faced in automation, I would say, were already mentioned in this presentation. This is the data. Data is one big thing. So the data must be reliable. That's why when the well tests are coming into the calibration system, they must be as accurate as possible at that point already. Also, I would say there is a lot of resistance to change that can be met at a site where the new project is implemented. And it's very important to be open-minded about changing the current business process, and in being open to designing something that would really generate the value. From the tools and process perspective, I would say this automation of well test, capturing QC and model calibration is already a very streamlined, a very well-known, at least to us, process. So the tools are all known. The challenge is really to make it work in the context of current business process of the client.
Yeah, thank you. We have more questions coming in. Will user have a flexibility to select only a couple of matched parameters instead of all the matched parameters given by the process? Because user knows the field and he or she has more idea about what parameters are changed.
Yeah, that typically depends on the design of the model calibration process. It depends on which solution space you're giving to engineers, essentially. So this is something that can be designed beforehand. There is always a possibility to overwrite automatically generated results with engineering judgment. It just needs to be included into the design process.
By adding more steps of validation, you are actually adding more manual steps, means more time. You're losing the importance of automation. Is that correct?
In a sense, but it depends on how critical this feature is for the client. Of course, we need to find a sweet spot between not stalling your system on every QC step and having enough control over it from the engineers, especially in the beginning of this of implementation of the new approach, so engineers feel in control of it.
Yeah. Okay, one more question. There are two generic approaches to the well test validation: matching the model to the well test and validation based on the amount of model tuning, or alternatively to adapt the well test to match the model outputs and perform validation based on the observed discrepancy. What do you think about both approaches and their pros and cons?
Yeah, in my opinion, it really depends on the operations and how historically it has been done in the field. One model or another would be a preference. I would say that the models are, you know, these are models. They are not, we make them represent the reality and we make them tune to the data that we can rely on. So I would say
if the well test data is good, then you trust that and then make the models reflect that.
Yes, that is correct. But it depends on how much the models are needed. I would say how much predictive power they still have if they if the well test was tuned to the model, not the other way around. So in my experience, I saw more cases of having well model tuned to well test, providing successful results and really generating the tangible benefits in the field.
Thank you. One more question here. Which are the tools used to integrate for well test improvement and automate and predict well test?
Well, this is a very broad question in general, because I can answer in a simple way that these can be either custom developed tools. Definitely you can do anything custom developed, but there are also some out-of-the-box functionalities on well-established DOF platforms that also allow this kind of functionality. And in general, I would say that this whole process and the whole, I'm not going to come back to the slide, but the whole process of capturing well test to calibrating the model, this can be implemented within one platform. It can be implemented within 10 plus different platforms, depending on what kind of IT infrastructure is in place. So the advantage of reducing the number of platforms that is used is, of course, the efficiency of data transfer between them fully streamline and automate this process.
Yeah, you can go back to that slide. I think it is important to show it on those slides. Yeah,
it is this.
Yeah, so as Irina was saying, it all depends on where each of the data sits, and then having the right platform available to integrate it under one workflow engine that will help you do all the model calculations and calibrations. Okay, there's more questions coming through. Let's see. If we have faulty or poorly calibrated meters in the system, can we use this tool to improve well allocation? Does this process involve any integrated model like GAP?
The models can totally be used to improve allocation process. I think with this question, we're talking about slightly different things. What I presented really covered the model calibration piece, and the question appears to be more about well allocation, which
and virtual meters to some extent. Virtual
meters, yeah. So I would say there are always options to search for some meters that are more reliable, and using, for example, commingled tests to derive information about the wells with less reliable meters. So this may potentially involve integrated solutions like GAP. I would say there is a value in deriving allocation from multiple sources to really see what the well model is producing alone and how the integrated model results, like the GAP results, look like, because they capture more integrated physics in the field.
Multiple ways of calculating these virtual meters. For example, you can use the DP across the chokes. Some cases you can use other methodologies like test by difference, etc., etc. So depending upon what's available on the field, obviously you need to have at least one source of truth that is available for you to create a virtual meter, and then you calibrate it as you go along using that. Am I right?
Yes, that is correct. I believe the export separator is something that in absolute most of the cases can be trusted. When I was talking about test by difference, for example, there are other test by difference techniques that can also involve models and virtual meters. But then in this case, you assume, of course, that you rely on your model to derive production of the wells.
All right. One more question. What sorts of models are typically used? Pure black box or hybrid or based on first principles, etc.?
Yeah, the models that are used, in most of the cases, I saw either like physical model based on classical petroleum engineering concepts like vertical VLPs and IPRs, and data-driven models as well. So generally, the concepts that we were discussing today, they can be applied in a very classical sense, and they can be also applied with the same concept to data-driven models. Also, I believe if the well test is required for reservoir engineering analysis, for evaluating the reservoir and these parameters, this is going to be a slightly different application than what classical digital oil field is doing. However, it is fully valid as a concept to be applied to that as well.
Okay. Maybe one last question here. how important is it to build a QC and automation process from upstream to data to downstream models?
Yeah, first of all, it provides an opportunity to have control of the process and to know what is expected in the consequent steps. So if model calibration unit knows how the well test was QC'd on the previous step, there is a certain expectation and certain logic that can be built. The critical point is to have these consistent between each other. And this is not always the case. Sometimes the test QC piece of this process relies heavily on manual actions, and these can be later on changed. The well test can be modified. There can be some faulty data coming in, and in reality, it can be really anything. It can be wrongly punched in number, or it can be a transient state captured during the well test that is going to really skew the model calibration. So, but in these cases, theoretically, you can also put additional stage gates on the model calibration. Yeah, but this is going to stall the system a little bit. So this is going to take away the advantage of full automation, because your model is going to be validated, but then engineer would need to go and manually still approve that this is a correct validation based on the insights that we provide to engineers.
Okay. That's end of our webinar. Thank you. If you have any more questions, please feel free to send them by email and we will answer them. I think I asked all the questions that were posted on the chat. Okay. Thank you very much for joining today. Appreciate you taking time, especially those who are joining from across the globe in a different time zone. Thank you, Irina. Have a good day.
Everybody.